Good day, everybody. How are you all? This is Dr. Nandi. Today we are going to talk about goodness of fit test. So I will share my computer screen with you. The percent of Americans with type O blood is 43%, A is 40%, B is 12%, and AB 5%. So 43 plus 40 is 83 plus 12 is 95 plus AB is 5%, 100. At a recent blood drive at a large university, the donors were classified as shown below. At the 0.05 level of significance, is there sufficient evidence to conclude that the proportions of the university blood drive differs differ from those of the general public? Okay. So first, we will total the number of donors at the university blood drive, which is 60 plus 65 is 125 plus 15 is 140 plus 10 is 150. Okay. So we are going to use chi-square goodness of fit test. Goodness of fit test. Sometimes called chi-square. Although it is written as CHI, it's not pronounced as chi, it is chi-square, which is written as like this, GOF test, goodness of fit test. Okay, so what is our null hypothesis? The proportion of different blood donors or different groups of blood donors is same or proportion, so it should be R, are same as that in the general public. In the general public. That means we are assuming O type will be 43%, A type will be 40%, and I'll create some more space. B type 12%, B type 12%, and AB is 5%. Okay, now let me create some space. And that's your null hypothesis. So the null hypothesis states that the proportion of different groups of blood donors are same as in the general public. Okay, and the alternate hypothesis at least one of the proportions or one of the proportions of the blood groups portions of the blood groups at the university is different from that in the public. Now I have to create some more space. So okay. So let's create a table of types of blood observed and expected. So this is the observed counts, and these are the expected counts. So basically, I have a table with 3 columns. So the first type of blood is O. Observed count is, so I have to move. So observed count comes from the blood drive is, let me fill up the observed count now, 60. And what will I expect? My expected count will be the proportion in the null hypothesis, which is 0.43, 43%, times the total number of blood donors, which is 150. And that will be equal to 150 comes from the sum of the total number of blood donors, okay? And that will be 0.43 multiplied by 150, which is 64.5. That would be my expected counts in O type of blood if the null hypothesis is true, because O type is 43% multiplied by the total number of blood donors is 150. Okay. Next, we will do for the A type. A is for observed count is 65, comes from the table here. Okay, from this table. Okay, 65. And what is my expected count is 0.4 times 150 is equal to 60. Okay, and then comes my B type of blood, and the observed count is 15. The expected count is 12%. Okay, so 12% is 0.12 times 150, which is 0.12 times 150 is 18. Okay, and then AB type. Observed is 10, expected is 5%, which is 0.05 times 150, which is times 150 is 7.5. 7.5. So this is 7.5. Okay. So this is my observed count and this is my expected count. Okay. Now let me create some space. So I have to calculate the test statistic. My test statistic is chi-square. Test statistic. Remember, test statistic is a comparison between the observed count and the expected count. Okay. So the test statistic in this case is chi-square, which is given by sum of observed. This observed count is called O. The expected count is called E. Observed minus expected count square divided by expected. Okay. Okay. And with K minus 1 degrees of freedom. Now K is number of categories. Number of categories. Okay. Here K is equal to 4 types of blood categories. Okay. Now, this symbol is summation, is sum, also called sigma in Greek language. Okay. Do I have to do these calculations by hand? No, we can use the calculator. Okay, so how do we use the TI-84 calculator? So, so we'll create some space. Okay, use TI-84 calculator to do chi-square goodness of fit. It is called goodness of fit because we are comparing the observed counts with the expected count. How good the observed counts come close to the expected count. That is where the name goodness of fit comes from. A fit test. Okay. So the first thing we will do is clear the memories of the calculator. And we press the second button, then plus button, then number 4. Then we will get clear all list on the calculator screen and then hit enter and done. This step clears the memory of the calculator. Step clears the memory of calculator. Memories of the calculator of TI-84. Okay. So let's do that. Second plus and 4. Okay, we get done. Okay. Now we will press the stat button. Press the stat button. And then number 1, which is edit. Okay. Okay. In L1, enter the observed counts. Observed counts. And in L2, the expected count. Expected counts. Okay. So let's do the L1 first, which is 60, 65, 15, and 10. Okay. Then press the right cursor key to move to the first line in L2, where we will enter the expected counts, which is 64.5, 60, 80, 18, and 7.5. Okay. So we have the observed counts in L1 and the expected count in L1, I mean L2. Observed counts in L1, expected counts in L2. O in L1, E in L2. Then press the stat button. Stat. Then highlight test on the top row. And scroll down to chi-square GOF test. First is chi-square test, next is chi-square GOF. As I told you, GOF means this is GOF, goodness of fit. Scroll down to chi-square GOF test. Okay, you're observed. So I'll create some space here. This is the screen you're going to see. Observe it, observed. already said observed is L1, expected is L2, already said, okay? Degrees of freedom is what you have to take into account. That's what you have to remember. So here the degrees of freedom is 4 minus 1 is 3. That's what you need to type in. Degrees of freedom is 3. 4 is the type of bloods. 4 minus 1 is 3. Okay. And then we scroll down to calculate. And hit enter. We are looking for the test statistic and the p-value. So the test statistic chi-square is equal to 2.06. 2.06. And look at the p-value is 0.559. Alpha value given to us is 0.05. P is greater than alpha. This is the p-value. Remember, p-value is the probability of getting a test statistic as extreme as 2.06. So decision, do not reject H0. Conclusion, at alpha equal to 0.05, there is not enough evidence to support HA. To support HA. Okay, because we did not reject H0, we did not support the alternate hypothesis. Okay, I will stop here today. If you have any question or comment, please write me a note. I'll get back to you as soon as possible. If you like this video, please give me a thumbs up. I really appreciate that. If you like this video, please share this with your friend. You and your friends, please subscribe to my channel by hitting the red subscribe button at the bottom right corner. I'll come back next time with another interesting problem, interesting solution. Thanks for watching. Take care. Have a nice day. See you next time.